All right, welcome back. So today we are basically becoming scientific detectives. Our mission? To see the unseeable. We're going to figure out how scientists can actually identify the tiniest building blocks of our world. I'm talking about things millions of times smaller than anything you could ever hope to see with a microscope. I mean, just think about that for a second. Everything, and I mean everything around you, the air you're breathing, the water you drink, even the very screen you're looking at right now, it's all made of these trillions of unique molecules. So how in the world do we tell them apart? How does a scientist know for sure that a new medicine is actually pure or that a water sample is safe to drink? You can't just look at it, right? You need a totally different way of seeing. Okay, so to crack this mystery, we're going to need the right tool. We need a technique that can practically force these little molecular structures to give up their secrets. And that tool is called spectroscopy. No, I know, it sounds a little complicated, but the core idea is actually beautiful in its simplicity. It's really just the science of using light to interrogate matter, to ask it one simple question. Hey, what are you? So, how does this whole interrogation work? Well, it really just boils down to three basic steps. First, you start with a light source. Then, you shine that light straight through whatever sample you're trying to figure out. And finally, you analyze the light that actually makes it out the other side. And here's the key part. The molecule inside that sample is going to interact with the light in a very specific way. And the pattern of that interaction, that's what reveals its true identity. So, let's start with our first tool. This one looks for the most obvious clue you can imagine. Color. It's a technique known as UV-Visible spectroscopy. You know, this simple idea actually explains something we see all the time, every single day. The color of an object isn't really about the light it keeps, it's about the light it rejects. Think about a blue shirt. Why is it blue? Because it's absorbing all the other colors, the reds, the yellows, the greens, and it's bouncing that blue light back into your eyes. Well, this technique does the exact same thing, just way, way more precisely. It tells us exactly which wavelengths of light a molecule's electrons are absorbing. But this brings up a pretty obvious problem, doesn't it? What about things like water or salt? I mean, what about the countless substances out there that are totally clear? Our color clue is completely useless here. So we're going to need a more powerful tool, something that can see what's unique about a molecule, even when it has no color at all. And that brings us to our next, more powerful technique. Infrared spectroscopy, or IR for short. This is the one that works on all those colorless molecules because it reads something incredibly specific about them. Okay, so let's compare these two. UV/visible light, the one we just talked about, has enough energy to make a molecule's electrons literally jump around, and that's what creates color. But infrared light? It's a little less powerful. It's not strong enough to make those electrons jump, but it has the perfect amount of energy to make the bonds between the atoms shake and bend and vibrate. It's kind of like ringing a bell instead of trying to lift it off the table. And that is the absolute core concept right there. Think about it. Just like no two people have the exact same fingerprint, no two different molecules have the exact same pattern of vibrations. It's totally unique. So by reading those vibrations with infrared light, we can identify a substance with unbelievable certainty. It is, quite literally, its molecular fingerprint. It's the definitive ID. Okay, so we've got one technique for color and a totally different one for vibrations. On the surface, they seem pretty different, right? But what if I told you they're both governed by one single fundamental principle? Because when it comes right down to it, it's all about the electrons. This big, unifying idea is called electronic spectra. And it's not some new tool. Think of it more like the official rulebook for how light and matter interact with each other. It's the science that explains why everything, at the end of the day, comes down to electrons. When that UV light makes electrons jump, we see color. And when IR light makes the bonds vibrate, well, it's the electron clouds that are holding those bonds together that decide exactly how they're going to vibrate. So maybe the best way to think about all this is that UV/visible and infrared light are just two different ways of asking a molecule a question. You're basically saying, hey molecule, what does it take to get your electrons excited and jump around? Or you're asking, what kind of energy makes your bonds start to wiggle and vibrate? But here's the kicker. No matter which question you ask, the answer you get back is always written in the exact same language, the language of its electrons. It doesn't matter if they're jumping to create color or if they're influencing how the bonds vibrate. Understanding what those electrons are doing, That is the key to understanding the entire molecule. Okay, so this is all really cool science, for sure. But what does it actually do? I mean, why should you care? Well, it matters because these techniques are working silently all around us every single day. Seriously, the applications are just everywhere. Think about it. When a company creates a new life-saving drug, how do they prove it's 100% pure? Spectroscopy. When an environmental agency tests your drinking water, how do they find those invisible pollutants? Spectroscopy. It's used in forensics to identify a single tiny fiber from a crime scene. Heck, it's even used by astronomers to figure out what stars light years away are made of. It's amazing. And the scale of this, it's just staggering. I mean, to date, scientists have identified over 24 million unique chemical substances. A massive chunk of those discoveries, of those confirmations, were only possible because of these very techniques, because we finally learned how to use light to read a molecule's fingerprint. So we started this whole thing with a pretty simple question, right? How do you see the invisible? And it turns out the answer was to use light, not to look at something, but to look through it, and to learn how to read the story that it tells. It really makes you wonder, doesn't it? What other secrets are hiding all around us, in plain sight, just waiting for us to find the right kind of light to finally reveal them?